Okay, moving on with our little examination of limits in one dimension. We've looked at the formal definition of what a limit is. We looked at a bunch of limit laws that can be derived from that definition. And so today we're going to start looking at limits involving infinity. So first, we've already seen a couple of examples where a limit does not exist. For instance, with the Heaviside function, 0 if t is less than 0, and 1 if t is greater than or equal to 0. So that just looks like this. It's a step function. So this limit, the limit of that function as t approaches 0, doesn't exist because from this way it's 0, from that way it's 1, so the two side limits are not equal. That's one way that a limit can not exist. Another function we looked at was sine of pi over x, which the limit of that as x approaches 0 also does not exist. And it didn't exist for a different reason, because even though sine is always a value between 0 and 1, in this case, as 0 gets closer to, or as x gets closer to 0, sine, this number gets bigger and bigger. And as this number gets bigger, sine goes up and down. So as this gets closer and closer to 0, this function just starts waving wildly in and out without ever landing on a number here. And then coming this way, it does the same thing, and it just goes faster and faster as we get to 0. But no matter how close to 0 you get, it's always going to have every value between 0 and 1. So again, the limit here doesn't exist because you cannot narrow it down to a single point. Okay, so today we're going to look at something else. What about the limit as x approaches 0 of 1 over x squared? So as x approaches 0, the denominator gets smaller and smaller. That means that this number gets larger and larger. And you can see that I made a little table here. You can see on this table that as you get closer and closer to 0, 1 over x squared gets bigger and bigger. So because of that, again, this function at 0, it does not approach a certain number, because as you get closer and closer to 0, it just keeps getting bigger and bigger. It looks like this. It goes up that way, and it goes up that way. So as x is approaching 0, this function does not approach a specific number. So again, this limit does not exist. But what we're going to look at today is that this limit does not exist in a particular way. This limit is different from the first two we looked at. It's not just a step function, and it doesn't just weirdly not settle on a value. Something else is going on here. And to indicate this kind of behavior, we write that the limit equals infinity. And note that this does not mean that infinity is a number, and it does not mean that this limit exists, okay? Rather, what this means is it indicates a particular way that the limit does not exist, which is that 1 over x squared can be made arbitrarily large by getting x closer and closer to 0. So in general, we'd say that the limit as x approaches a of f of x equals infinity. So it's interesting just to notice that when the limit behaves in this way, we have a special symbol for it. When it behaves in this way or in this way, we don't have a symbol for it. That tells us that there's something special or important about this particular way of not existing, which we're going to label infinity. So what we say here is that the values of f of x can be made arbitrarily large by taking x sufficiently close to a, but not equal to a. So that sounds almost exactly like the epsilon delta definition of a regular limit, right? And it is. Infinite limits can be defined in a precise way that is very similar to how we defined limits. So here's the precise definition of an infinite limit. Let f be a function defined on some open interval that contains the number a, except possibly at a itself. Then the limit as x approaches a of f of x equals infinity means that for every positive number m, there is a corresponding delta such that f of x is greater than m whenever x minus a is less than delta. So what this means is, this is almost exactly like the delta epsilon definition, except instead of epsilon, we have m, and instead of less than, we have greater than. So it's very interesting because the epsilon definition, when we have an actual limit, says that no matter what epsilon you pick, no matter how close an interval you make to f of x, we can find a delta such that if x is closer than delta away from a, then f of x is going to be closer than epsilon away from L, okay? So this is the same thing, except it's the opposite. So here what we're saying is, if you graph this, just make a picture of this. If we have this function again, there's some line here that is the value m, and we're saying that no matter how, so here is a, and then there's some delta here, okay, that no matter how big you make m, you're still going to be able to find a delta that's small enough that every value of f of x inside this interval is going to be higher than that number. And remember, we can think of this also just as an interval here, where x is an element of a minus delta, a plus delta, but x does not equal a. So you can see that if, as m gets bigger, you'll have to make delta smaller, you'll have to make the interval smaller, but then once you're in there, everything is going to be bigger than m. So let's use this definition to prove that the limit as x approaches 0 of 1 over x squared equals infinity. So we do it the same way. First guess, whoops, and then prove it. Remember, what we need to do is find a rule. What we're actually looking for is a rule, so that any m that you give me, I can plug it into my rule and return a delta that will make the statement true of any x inside that interval. So the first thing we have to do is just guess what a rule might be, and then we'll prove that that works. So given m greater than 0, we want a delta greater than 0 such that 1 over x squared is greater than m whenever x minus 0 is less than delta. So this is 0 because in this case, the limit is at 0, okay? So 0 is a in this case, so it's x minus a is less than delta. So we can rewrite it that multiply the x squared, divide the m, and we have that 1 over m is greater than x squared whenever 0 is less than the absolute value of x is less than delta. So now if we just take the square root of both sides, and I'm just going to flip it around. So if we take the square root, we have the absolute value of x is less than 1 over the square root of m. We can say the absolute value of x because whether x is minus or positive, if we square that, it's going to be x squared, right? It doesn't matter. So if we take the square root, then the absolute value of x is going to be less than 1 over the square root of m, again, when 0 is less than x is less than delta. And now we've done what we need to do, because here's absolute value of x, here's absolute value of x. So if we set delta equal 1 over the square root of m, then this should work. Okay, that's our guess. So now we have to prove it. If m greater than 0 is given, then let delta equal 1 over the square root of m. So we need to show that 1 over x squared is greater than m when 0 is less than x minus 0 is less than delta, which equals 1 over square root of m. So if the absolute value of x is less than 1 over the square root of m, then if we square both sides, that means that x squared is less than 1 over m, right? We squared both sides. Then we rearrange them. That means that m, so multiply both sides by m, divide both sides by x squared, and we have that m is less than 1 over x squared. And that's what we needed to show, right? We needed to show that 1 over x squared is greater than m whenever x is less than 1 over the square root of m, and we just showed that, because if this is true, then m is going to be less than 1 over x squared. Okay, that's it. So since we've proven this fact, then that means that the limit as x approaches 0 of 1 over x squared equals infinity. Okay. Now, the same actually works when f of x gets arbitrarily large negative as x approaches a. So then we write that the limit of, as x approaches a, of f of x equals minus infinity. And so again, this isn't a number. We're just saying, this is just a statement of what happens to f of x as x approaches a. And what that looks like is it's just basically the opposite. It goes down like this. So if this graph was the limit as x approaches 0 of minus 1 over x squared, then that equals minus infinity. And so we have a similar precise definition as well. So the precise definition of minus infinity is, it's just the same as the positive infinity. The limit as x approaches a of f of x equals minus infinity if, for every n less than 0, f of x is even less than that whenever x minus a is less than delta. Okay, and you can see, so it's the same as the last graph. If we have a line here, n, no matter how low we make this n, if you just get the interval close enough to a, then everything in f of x will be below that line. Okay, same thing. Okay, so these definitions also work for one-sided limits. We can say that if we're only approaching a from the left, then f of x could be infinity or it could be minus infinity. And the same way, if we approach a only from the right, it could be infinity or minus infinity. Okay, so one more definition, vertical asymptotes. The line x equals a is called the vertical asymptote of the curve y equals f of x if at least one of the following is true. So basically, if at a, f of x approaches infinity or minus infinity, either from a one-handed limit or the full limit, if the function is approaching infinity at that point, then it's called a vertical asymptote. So for instance, with our function 1 equals x squared, at 0 it goes up like that. So here, y equals 0 is the vertical asymptote because the limit as x approaches 0 is infinity. So finding the vertical asymptotes of a function is helpful for graphing the function. But also, and more importantly, they're fundamental to complex analysis, which again is where we're headed. This is what we're working toward with multivariable calculus. But basically, you might have, where we're going is, you might have a surface here. And there's a point here where it goes up to infinity. And when we get to integrating this function, what we're going to be doing is just like in one-dimensional calculus, remember when we integrate, we're looking basically at the area under this curve, right? That's one way to think about it. In multidimensional calculus, it's the same. If you have a two-dimensional surface that sort of is in this domain, you can look at the surface, you can look at the volume under this curve, under this surface, okay? But it's possible for the surface to go up to infinity at some point, to have an asymptote here. That breaks our ability to integrate in one dimension. Complex analysis resolves this problem. Because complex numbers are two-dimensional in some sense, complex integration allows us to simply go around the hole. Isn't that interesting? Now, all this is way more complicated than I'm saying here. This is just to give us a taste of what's coming, but basically that line in one dimension becomes a surface in two dimensions. I said this when we were first looking at calculus, how, remember the fundamental theorem of calculus is that if you just look at the value of the function here and the value of the function here, and you subtract those two, then you can get the total rate of change between those two, right? This is the fundamental theorem of calculus, which is the amazing thing is that if you take the antiderivative of the function, then all you have to do is take the two endpoints and you can find out the total rate of change between A and B. Where we're going with multivariable calculus is that the same thing is true in multivariable calculus. If we want to find the volume under a surface, we don't actually have to look at the whole surface. We don't have to count every change. We can actually just look at, sort of integrate around the area that we want to integrate over, And in some way, the same way that these are the boundaries, you just add up the boundaries. The same thing works in multivariable calculus. Basically, if you add up around the outside of the surface, you can find out what's going on inside the surface. It's the same thing. But what the problem with that is, it doesn't always work. If the function goes up to infinity somewhere, it won't work. Complex analysis allows us to go around these discontinuities. Basically, you can integrate around the problem and just remove it. So that even though this surface goes up to infinity at a point here, using complex analysis, it's actually possible to get rid of that hole and find the volume under this surface anyway. It's really interesting. That's just the tip of the iceberg, but that's one of the basic points. Just like the square root of a negative number does not exist in reals, but does in complex numbers, the complex numbers are like this shadow realm that allows us to move around the problems with real numbers. So this is called a pole. And then if you remember, moving on to Weierstrass, Weierstrass are the doubly periodic functions that have a pole at every vertex of a parallelogram. So that means that it goes up here, and only there. So it's smooth everywhere else, and it only goes up to infinity at the corners. And with that, we're going to be able to integrate it. And then this, again, insanely, is what leads us to our connection with elliptic curves. So I just wanted to point that out, that these asymptotes, there's a reason that this behavior has a symbol, whereas this behavior doesn't. Because this is super important and special, and it's sort of one of the main topics of complex analysis. And of course, it's not only important to complex analysis, it's also important to projective space, for example, which also, of course, leads to Fermat's last theorem. Okay. Let's look at a couple of examples. So let's find. So we're not going to calculate these, I just wanted to look at the behavior of these. So in this case, if x is approaching 3 from the right, whenever x is bigger than 3, then the denominator is bigger than 3. As x is getting closer and closer to 3, then this number is getting smaller and smaller, but it's always bigger than 0. So this number is getting closer and closer to 0, but always positive. So as the denominator gets smaller and smaller, this number gets bigger and bigger. So we can see that just intuitively that the limit as it approaches from the right equals infinity. But then look what happens if we approach it from the other direction. If x is less than 3, then this number will always be negative. So even though as we approach 3, it's going to get closer and closer to 0 again, it's always negative. So this number is getting smaller and smaller. That means this number is getting bigger and bigger, but the denominator is always negative, which means that it's getting to be bigger and bigger in a negative direction. The limit as x approaches 3 from the left of 2 over x minus 3 is minus infinity. And so now with this information, it'll be easier to sort of get a picture of what this graph looks like. So we have at 3, when x equals 3, the graph goes up this way and then down this way, okay? As you approach 3 from the left, it gets increasingly negative. As you approach x from the right, it gets increasingly positive. Okay, what are the vertical asymptotes of f of x equals the tangent of x? Well, we know that tangent x equals sine of x over cosine of x. So there are possible asymptotes whenever cosine of x is approaching 0. So in fact, cosine of x approaches 0 from the right as x approaches pi over 2 from the left. So let's think about this. So what this means is, when we have a circle, when x is 0, cosine is 1. When x is pi over 2, cosine is 0. And then when x is pi, cosine is minus 1. So as we increase x toward x minus 2, cosine is getting smaller. So if we have the graph of cosine, cosine starts here at 1 at 0, and it goes down to 0 at pi over 2. So as we're approaching pi over 2, cosine is getting closer to 0. So remember here, this notation, it's really important to keep in mind what this means. It doesn't mean that it's negative or positive. It's the direction that you're coming at it from. So what it means is that when we're approaching from the left, it means that we're under pi over 2 and coming at it from the left. So we're getting bigger toward pi over 2. So that's what this means. As that's happening, then cosine is getting smaller. It's going from 1 down to 0. So as x is going this way, cosine is going down toward 0. So as x approaches pi over 2 from the left, then cosine is approaching 0 from the right. But then as x approaches pi over 2 from the right, then cosine x approaches 0 from the left. This is the graph to look at. It's approaching from the left, or if it's approaching from the right, then it's already negative and getting closer, okay? Now sine of x is 0 when x is 0, and it's 1 when x is pi over 2, and then it's 0 again. Sine is always positive around pi over 2. It doesn't matter which direction you're coming at, it's always going to be positive. So what that tells us is, as we approach pi over 2, sine is always positive. That's no problem. But cosine is approaching 0 from the right as we approach pi over 2 from the left, and it's approaching 0 from the left as we approach pi over 2 from the right. So we can write that down to say that the limit as x approaches pi over 2 from the left of tangent x, okay? So what does that mean? If we're approaching it from the left, then the denominator is approaching 0, so that means this is getting bigger and bigger. And sine is always positive, so then positive over positive, so it's going to be going up because the cosine, the denominator is getting smaller, so this is getting bigger. So it equals infinity. And then if we approach it from the other side, then cosine is again approaching 0, but now it's negative. That means that this whole thing is negative and getting bigger, so it's going downward. So what we've seen here is that pi over 2 is an asymptote. We can do the same reasoning to see that actually every 2n plus 1 multiple of pi over 2 is going to be an asymptote. So this is an asymptote, this is an asymptote, and then there'd be another one here, minus pi over 2, and so this is what tangent looks like. It goes down to minus infinity as you approach from the right, and it goes to positive infinity as you approach from the left. Okay, cool. One last example. What if f of x equals the natural log of x? Now, in this case, f of x only exists when x is greater than 0. When x is less than 0 in real numbers, then this value does not exist. So in this case, it's only a right-hand limit. So it's not even just that it's different depending on which direction you approach it. The function is not defined less than 0. So here we just have that the limit as x approaches 0 from the right of ln x equals minus infinity. So sometimes the function isn't even defined in one direction. Sometimes they go in the same direction, sometimes they go in opposite directions. But in every case, those are vertical asymptotes, and it's going to either infinity or minus infinity. So just to remind you, in every one of these cases, this limit does not exist. The limit is not minus infinity. This is the symbol that we use to say that this limit does not exist in a particular way. Okay, so that covers the case where the graph of a function goes to infinity at a specific value of x. But that's not the end of the topic of limits involving infinity, because we also need to look at something you may have noticed that we haven't talked about yet, is limits as x approaches infinity. And we'll do that next time. Then we'll do continuity, we'll be done with one-dimensional calculus, and we'll move back to multivariable. Thank you.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe. And please join me on Patreon. The link to that is below in the description. Thank you.